this a separate one. Okay, just about ready to start. We were fewer this week, so how are things going? Shaking heads?
It's worse.
Okay, it's worse this week.
Yeah, it just keeps on getting worse.
Okay, that's good. That's that positive attitude that we enjoy from doing mathematics. Sure, we'll try improve the situation.
Someone in class who actually got something said that they had to go to lectures and watch lecture videos.
Okay.
And I go to lectures. I don't watch lecture videos. But now maybe I'm going to start watching.
Okay. Are all your lectures recorded?
Pardon?
Are all your lectures recorded? Or did they mean watching lectures from another course?
Oh no, like for math.
Yeah.
For the
I just thought maybe
specifically the section. It was like, I think it helped because I actually also watched lecture videos even though I was here.
Mm-hmm.
And I was like, okay, maybe I'm going to start doing that because, yeah, I know.
Yeah. Typically, it's just like the more times you can go through it. The other thing I would say, although maybe I can look around a bit, but it's useful to see if you can see sort of the exact same content, maybe just presented by another person at another university, like on YouTube. Because also that's nice. You can just, I understand this part, skip ahead, or watch on 1.5 speed, and then like slow down, repeat, like when you need. The problem with that is like which university, because there's like a lot of this content out there. So maybe I can look around and see if there's something. Let's see. Yeah, okay, I'll try to think about that. But yeah, I do recommend like the more times you can see it and in slightly different ways, the better, the more solidified it will be. Maybe maybe the lecturer used a slight difference of presentation when they were first putting it up, and then you see someone else do it slightly different, and you're like, oh, okay. And maybe that's all you need for that particular idea to click. The more kind of clicks that you have like that, the happier we become.
Yeah, and also there's like, I don't know, I feel like maybe it's just me. There's like
it's almost certainly not just you.
Between like tutorials and lectures.
No, that's almost certainly not just you. Not to kind of overrule you, but first of all, there'll definitely be a lot of people feeling that way, and that's just like me talking to different people. Like I know that for a fact right now, and also just having done this course for several years. It's always like that. Big picture is actually like we probably don't have the best kind of course design at UCT. We don't have the worst course design, but we don't have the best. And what I mean by that is like our curriculum is sort of fine. It's pretty standard internationally, but the way that we evaluate things is a little bit rough. And so I sympathize with that a lot. And what I mean by that is you kind of hear a bunch of abstract ideas in a way that you can ask questions, but you're not really having a back and forth with the lecturer and lecturers. That's just pretty normal. There's just too many people, and you don't really know what to ask always. You go to the tutorial and it's like, okay, I don't know what to ask. I need to spend the time at the tutorial figuring out what I even don't know. And already by then, you're on to the next tutorial each week. And then you only have 2 evaluations, right? Like test, so you don't get a lot of feedback. That would not be my personal preferred design, but changing stuff like that is a whole long discussion that is not really relevant to the purpose of, but just to tell you, like, you are going to do worse in math if you say I'm the only one. Okay, like that's just a fact. You can reproduce that over and over again. So if you feel like you're the only one who doesn't get it, or you're the only one who doesn't like the way that the tutorials are set up, that's just not true. Okay. But we should move on from that and try our best with what we have. And then write in the course evaluation, say in the course evaluation, I'd rather have more one-on-one tutoring, or I'd rather have more continuous assessments to get feedback. Really ideally what would happen is you'd have sort of a small assignment every 2 weeks or every week, that's really not worth a lot of marks. So like if you do fall behind a little bit, it's not like terrible. So it's not supposed to increase the overall workload, but then you also get a lot more continuous feedback. But then to do that, you have to employ more tutors, and somebody also high up has to say, we're doing that. They have to make the decision. So, and it's not a popular decision, but it probably would be better. So I sympathize. That's all I'm saying. But write it in the course evaluations. I strongly encourage that. Okay. All right. So I think so. You had a request to discuss the algebraic limit theorems for combining functional limits, basically. So we had these things that said that, like, if I have two sequences that converge and I add the terms together, then they converge to the sum of the limits and stuff like that. We have the same thing for functions. So there's a request to, can we kind of just look at that? I think we will do that, but I just want to clean up some of last week's stuff first, if that's fine. I hope that's fine, or are we, unless we're like super happy and comfortable with all of the basic stuff with limits. Okay, so let's go there, and just please feel free to shout out like, oh no, we get this, or please go slower. Like any of that kind of feedback is helpful. But so let's sort of say last time, at the start at least, we kind of wrote down the definition. We were saying that, like, what did we mean in first year when we wrote something like this? Well, really formally, as what we're going to say, that the definition of what this kind of notation means is that sort of roughly, okay, we said roughly in words, x close to a means f of x close to L. And then we wrote out this really formal definition that said exists a delta greater than 0 such that x minus a less the delta, and I probably should tell you something like the domain of f. So f is like a function from some set. I'm just adding this week to be a little more careful, but we want to say that whenever x is close to a, and particularly which x's, the x's that are in the domain of f, it implies, actually let's write it down here, it implies that f of x minus L is less than epsilon. Okay? So we have an intuitive idea for what this is saying, and then we wrote down this really formal definition. And the point of this is so that we can actually prove things, and we want to get to the point where we can actually use this as a tool. It looks a bit ridiculous the first time you see it, as how could that be a tool that helps me? It looks more like it obscures things than helps, but it is actually a tool that we're going to use. And yeah, so we just need to practice and really make sure we feel good about it. And there was this little caveat. I don't know, did they say this in lectures, that your A has to be a limit point or an adherent point, or did they use a word like that at all? They did something like that? So we'll just say here in parentheses, this is not really the focus of what we're writing down, that A is a limit point of A. Okay.
Could you please just briefly
review limit
what
point?
you said about the difference between limit and isolated point?
And the other point?
Isolated point.
Oh, an isolated point. Okay. So a limit point is basically saying, one way of saying it is just like, there are infinitely many points in this set A that are arbitrarily close to that point. Another way of saying that is like I have sequences in A, like where all the terms are in A, that converge to that. Okay, so if I have to draw on the number line, if I drew something like 0 to 1, the open interval, and then I have this isolated point 2, and I said that, okay, my A is going to be 0 to 1 open interval union the isolated point 2, okay? So pretend that's my A. Any point in here is a limit point. Why? Because there are like infinitely many points arbitrarily close to any point in here. Now that's just me saying it in words, but if we went back to our definitions, we would have to look for sequences that converge to points here. So you can imagine if I just pick the point here, and I ask, is there a sequence in A that converges to that point, and the terms of the sequence should be different from that point, you could say yes, there are. I could imagine that there's some sort of sequence. Maybe I should have yellow chalk. A little bit low on yellow chalk, but you could imagine if I'm picking this point to be little a, I could definitely find a sequence where all of the terms in the sequence are different from little a, they're in this set, and they converge to little a. Okay, that doesn't seem implausible, and we can work hard to like kind of show that for this set, but I hope that's just sort of an intuitive picture. Then I could ask you, like, what about, say, this point 0? Like 0 is not in the set, but is it a limit point? And the answer is yes, because we can have like sequences that converge where all the terms in those sequences are in A and they converge to 0. One of those would be like 1 over n, right? 1 over n is definitely all in the set. Okay, maybe not the first term. And it converges to a point, to the point 0. Okay, so 0 is a limit point of the set as well. And then you could ask, okay, what about 1? So you're starting to get the picture, okay, 1 is also a limit point. It's kind of saying the idea that it's like, there are infinitely many points in this set that are arbitrarily close there, which is the same thing as saying that a sequence that can make the set of numbers that converge to that point. And then we could ask, what about 2? So an isolated point. And 2 is just not a limit point. Because there's no way for me to find infinitely many points of this set that are different from 2 that are arbitrarily close to 2. Okay? There's no sequence in this set that is where the terms are different from 2, where that sequence converges to 2. There's always like this finite difference from all of the other points in the set. Okay? So basically we want to think of like limit points and isolated points as almost being the opposite thing of each other. That's one way of sort of saying it. Is that kind of cool? And then the reason why we're saying in here, I didn't really mention this last time because I wanted to just kind of focus on the main ideas. The reason why we're saying that this A that X is approaching is a limit point of the domain of F is really that idea that like I want to be able to kind of I want to be able to pick lots of x's that are close to A, that are in the domain of X, that are in the domain of F. So hopefully if you kind of see in this picture, like if I had to draw some function f, and then I'm asking, here's my A, and I want to ask how does f behave as x kind of goes to A, I want A to be a limit point of the domain of F. I don't want, if this was the domain of F, let's say F is not defined over here, I don't want to try and think about what's happening if A was over there. Because sort of, that just doesn't capture the idea of what we're saying, right? We said originally, what did we want to study? We want to say, for x is close to A, f of x close to L. That's what we're looking at. If A is over here and f isn't even defined over here, then there's no way that I can talk about x's that are closer to A and study the behavior of f of those x's, because f just isn't defined for those x's. So that's why we're not going to worry about isolated points. We're going to make sure that this point is arbitrarily close to lots of x's that are in the domain of f. This is not really a particularly critical point. If it's unclear, we can talk more about it or check back on the recording or check the textbook, but this little detail here is not really that important. It's just sort of saying we don't want to consider limits of this function where the x's are not really, this A that we're considering the limit as x goes to, the function isn't really defined around that A. Maybe that's another way of saying it. If I want to study the limit of f where x is nearby A, then f better be defined nearby A. That's probably a much better way of saying it. And that's all that this does for us. Maybe some questions? I'm not sure if we're happy with that. Yeah?
Well, isn't it another requirement is x minus a must be greater than 0, strictly greater than 0?
Yes. So I wanted to actually ask you about that. So that differs between different courses, so I don't know how we define it in this course. So did we say that we want x to never be equal to A?
Yeah.
Okay, then yes. So you don't have to impose that requirement, but in this textbook and in this course, we'll do that, and everything will still work.
I don't know if I heard my lecturer incorrectly, but he said at the point where the reason why we strictly want it to be greater is because x is then equal to a, then it's an isolated point.
Yeah, so then you could define limits for isolated points, and then you would not use a limit point here, you would use another thing called an adherent point, and that's just a whole other story.
Also, that's why
Yeah.
in my lecture he didn't mention that a is a limit point, just because we have that.
Let me think about that. That might,
Because then we say that,
It
we
might-
said that, and then we said x is an element of a. Yeah, x, yeah, we said exactly like that, but we didn't mention this a.
we didn't mention that A is the limit point of A.
Yeah.
Of the, yeah, I think, let me just think about that carefully, but I think what you're saying probably makes sense to me, that if you just put this, then you don't have to worry about this, because you're already implying that x is never equal to A. Maybe I should come back to you on that, because yeah, I just don't have it right now, but I think I think you might need both, but I'm not sure. But yeah, the reason I left this out, don't worry too much about it. It's just you could have slight variations in these definitions. All the big theorems are still true, and it just kind of depends on the textbook you pick. And we've chosen to just go with this, and everything will work. So thanks for pointing it out, though. Okay, so I'm going to erase this. And let's just quickly agree on, one more time, what the picture of this whole thing is. So the idea, oops, we actually don't need it to look like that. Okay. The idea is here's my f of x, okay? And I'm picking some point A, and what I'm looking at is all the x's between a plus delta, I'm going to do this, and a minus delta, okay? And then this up here is going to correspond to L, and then we want to look at kind of L plus epsilon, L minus epsilon, this open interval. Okay. And all we're saying with this definition is that anytime I pick an epsilon, there should be some delta that I can kind of pull this interval in small enough that for all of the x's that are different from A in that interval, it has to be then true that the function evaluated at those x's is in this interval defined by that epsilon. And this is just quite similar to what when we drew pictures for sequences, where we took these kind of inequalities involving the absolute values, we removed the absolute value by saying that this is equivalent to like x less than a plus delta and x greater than a minus delta. That's this statement here. So here's my x's. And then I really need my f of x's to be in this interval. Okay. So all the y values have to be in that interval. So that's the picture. And that's just capturing the idea that we kind of originally started with. It's like, I want to say by this limit, I want to say that when x is close to a, f of x should be close to L. So I'm saying, what do I mean by close to a? There has to be a delta such that I can make x close enough to a, can shrink this interval in enough so that all of the y values are in this interval. And that's it. Okay, so now we wanted to do some examples, and last time we went a little bit astray, but we will clean that up now. Any questions on this so far? No? Okay. By the way, how was our tutorial this week in terms of just like, particularly question, I don't know if it was one or was it like sort of 1A, 1B, C, D? There were four questions there. What we're going to do now is similar. I mean, we can even work through one or two of those. Would we like to do that? That's basically what I'm asking. Yeah. maybe we can pick one, maybe two. So we could get a question like, show using the definition that that the limit of, what did we say, something like x goes to 2 of x squared is equal to 4. Okay, so from first year, this was just easy. We just...
Cubed is equal to 8.
You want to do that one? Okay.
Yeah.
All right. I hope it still works in all the ways that it should. I think it will. So first year we knew that we just, this is just some polynomial, so we proved that we're allowed to just kind of substitute in. There's no holes in the domain of the function. There's no places where it becomes infinite that we have to worry about nearby 2. So this is kind of an easy thing, but the question is, can we reproduce that with our definition? Just for some practice. I mean, the power of this definition is it allows us to treat harder things than this, whereas this intuition just wouldn't work there. And in fact, we need this definition to prove that you're allowed to do stuff like just substitute it. But we're just going to practice quickly and say, are we really comfortable with what's happening with the definition? Okay. So, the sort of outline for solving a problem like this would be kind of, always write down what you want to prove. And I'd say kind of plus rearrange the inequality involving epsilon, because you're always going to ultimately have to show that some inequality involving epsilon is satisfied. So I want you to rearrange the inequality involving epsilon to relate some part of it to the inequality involving delta. Okay, so we'll see what I mean by that in a sec. Okay, so that's step one. Step two. Let's say it this way. So when you're doing this, you're gonna find either that you can relate the inequality involving epsilon to the inequality involving delta directly, or you're gonna find that some part of the inequality involving epsilon is related to the part involving delta. So we'll see that now, but you might find that a factor, you might be able to factor the inequality involving epsilon into pieces where some factor looks exactly like the inequality involving delta, and then there's some other stuff. Okay, so then I would say part two, this is sort of really the critical step, is quite where most of the challenge lies, is derive inequalities for any left over for any leftover expressions where it's not obvious. Maybe I should say leftover expressions in the epsilon, kind of in the epsilon inequality, where it's not obvious how they relate to the delta inequality. Okay. And then 3, what we want to do is use min argument does argument have an extra E? I actually don't remember. Use a min argument so that all inequalities you derived are simultaneously true. Okay? And really what I mean by that is you're going to have found a bunch of useful inequalities and you want to put them all together so that you so that you finally get f of x minus L less than epsilon, which is our final goal. So it's a bunch of words, and it'll be very, very clear when we just do examples. But maybe this is useful when you look back on your notes to sort of categorize in your mind what are the 3 parts of what I need to be doing here, rather than just think of this one big sort of opaque problem. So the first thing we've always done, we did this with sequences as well, is we just write down what we want to prove, and then we try kind of rearrange it into a useful form. And we're going to do a bunch of examples to see what we mean by a useful form, because we want to build intuition for that. But typically what a useful form is going to be is like there's some inequality involving epsilon, there's some inequality involving delta. We want to turn the inequality involving epsilon to have pieces or the whole thing to be obviously related to the inequality involving delta in some way. Because remember, ultimately our goal is to find a delta. We need to show the existence of a delta such that some inequality that depends on epsilon is true. Okay? So we rearrange the inequality involving epsilon to try and help us find something related to the inequality involving delta. Then, if there's anything else, like maybe there's some different factors or there's some other stuff, when we rearrange this, like maybe there's one factor that's definitely related to the inequality involving delta, and then there's some other factor that we just don't know what's going on with it, that's where the bulk of our work is. We need to deal with that. We need to figure out what's going on with the piece that just isn't obvious how it relates to the delta inequality. And then once we have a useful inequality for that kind of bad piece, the not obvious part, we want to have both things be true. We want to kind of bound all the different parts of the expression so that we finally get something that looks like absolute value f of x minus L less than epsilon. And the typical way is you're going to have a delta that works for some inequality, like a delta 1, you're going to have a delta 2 that works for another inequality, and so on. And we need to use a min argument so that all of those things are true simultaneously. But okay, let's now just see what I'm talking about. All right, so we have this problem that we want to solve, and so solving this would mean showing that we want to show that for all epsilon greater than 0, there exists a delta such that x minus 2 less than delta implies x cubed minus 8 less than epsilon. Okay? This is sort of me just roughly writing down roughly what are we looking for. We need to find this delta such that whenever this is true, this is true. Okay? That's just me substituting directly into the definition of the limit. And now we said as part of like step 1, we need to rearrange this inequality involving epsilon to relate it to the inequality involving delta. Okay? And in this case, it's because it's a polynomial, trying to factor it is kind of useful. You might even notice that 2 is a root of this. If you substitute in 2, you just get 0. So definitely this has a factor x minus 2. So we'd write, notice that x cubed minus 8 is actually just equal to x minus 2. Okay, and do I remember how to factor polynomials?
Squared
Thank you.
plus 2a
Plus 2a. Minus 4?
plus 4.
Plus 4.
Let me make sure.
Yeah, let's just check. So x cubed plus 2x squared minus 2x squared, good. Plus 4x minus 4, and then, yeah, so that works. Okay, and this is the sort of thing I was talking about. We've now related the epsilon inequality to something involving the delta inequality and something else. Okay, and so if this piece wasn't here, we would basically just be done. We would just say like, oh, make delta and epsilon equal, because we ultimately want this to be less than epsilon, so we want this whole thing to be less than epsilon. But we have this extra piece here, so we want to bound this. We want this whole thing less than epsilon, so we want to bound this part, but we also want to show that this is bounded by something. Okay, and typically this is the harder thing to deal with, because we already see this appearing up here. Okay, so our hope, and I guess also we could, so our hope is now to use what we already know to bound this, or maybe I shouldn't say what we already know, but we should use the delta inequality to try bound this. Okay, and you'll see this pattern showing up again and again. So they like to do things like just say, kind of, you'll see in your lecture notes, I wouldn't write this down, this is not what I'm saying, but they'll just say like, suppose kind of x minus 2 less than 1, and then they do some stuff. Suppose delta is equal to 1. And it's true that you're allowed to kind of do that, because it may feel funny that you're looking for the existence of a delta, so why are you supposing that delta is equal to something? But maybe what we should do is just kind of rephrase what we're doing like this. We're like, we haven't proven anything yet, we're just investigating what kind of things are true. So we're saying like, what if there are some x's that satisfy this? Then what does that imply? We haven't yet put together any kind of full argument for showing that this guy is less than epsilon, but we might be able to kind of investigate this case. Now, I don't always go this way. I like to kind of just leave this undetermined. And then later on you might find, oh, choosing A is equal to 1 is useful, but for me at least, I find it obscures it less.
Sometimes it doesn't work when you say 1, so.
Exactly. So then you'd say, well, how do I know? Should I choose 7? Should I choose 17? Should I choose a half? Sometimes you need a smaller number. So we'll do another example after this, but I like just leaving A undetermined. I want to say, what if x is closer to 2 than A? Because remember, we're asking ultimately the question, what is the behavior of this function when x is close to 2? But now we also want to ask, what is the behavior of this function when x is close to 2? Okay? Because we know something about this factor. It's related to our delta inequality, but we're not sure about that factor. Okay. So I guess we could start just kind of spanning this out. I don't know if they have a faster way that they did it, but what I would do just roughly without knowing what to do is I would just say, well, this is equivalent to saying that x is less than 2 plus a, and x is greater than 2 minus a. Okay? So I just took away the absolute values, put a minus a and a plus a, and then I added 2 across the whole thing. And then that tells me how x squared behaves. Okay. So I kind of learn a bunch of different stuff here. So I'm going to say that this implies, because remember I'm trying to figure out how do I bound this? Okay. So I'm trying to rearrange this to look like x squared plus 2x plus 4. Again, I don't know if they had a faster way that they did this, but so what I would do is I would say, well, this implies two things. Kind of one, I can square this inequality. Let's just check that things are not negative. We can say 2 minus a squared is less than x squared, which is less than 2 plus a squared. Okay. And also I learned something about how 2x plus 4 behaves. So what I would do is multiply the whole thing by 2 and then add 4. Okay? So over here, I also learned that 4 minus 2a is less than 2x, which is less than 4 plus 2a. Okay? And then that implies that 8 minus 2a is less than 2x plus 4, which is less than 8 plus 2a. Okay? And then I would say that I can kind of organize this a little bit more clearly. So I use this inequality to derive this, and I use this inequality to derive this. So that I could kind of say, so then altogether, I know that kind of 2 minus a squared plus 8 minus 2a is less than x squared plus 2x plus 4 is less than 2 plus a squared plus 8 plus 2a. Okay. Now it looks a little messy, but we're just going to pick a in some convenient way pretty much now. Now, this little comment, just write this up here. Now this is kind of the messiest it's going to look, but don't get too thrown. I mean, we've just used algebra so far. Like, all we did is we said we knew something about x minus 2 less than a. We said if I had some a such that that was true, then what do I learn about that factor that I cared about? I'll just write that up here just so that, because we are going to use it again. So we said that x minus x cubed minus 8 less than epsilon was equivalent to saying that x minus 2 less than x squared plus 2x plus 4 is less than epsilon. Okay? So we were just trying to bound that second factor. So I've used that to get to here, where I have that second factor in between some numbers. But, notice I want x squared plus 2x plus 4 less than some positive number. But I only have an inequality involving x squared plus 2x plus 4. Okay? I haven't yet found out about absolute value of x squared plus 2x plus 4, sorry. I just have this inequality. Now, if this guy with a minus sign in front of all of it was equal to this guy, then we'd be done. Okay? Because this guy is definitely a positive number, if a is positive, always. So if this guy just had a minus sign in front of it over here, then I'd just say absolute value is less than this guy, right? Because we know how to undo and put back absolute values. But that's not the case. And in general, that just won't be the case. You'll notice that if I multiply this by minus 1, it's not equal to this, okay? But we can still deal with that with a little trick. And this, again, we're going to use this, you're going to see this over and over again, so this really isn't just sort of out of left field. It's something that you need to see once and then kind of use it over and over again. So the trick we're going to use is, but if the left-hand side is, if we have something like 0 is less than or equal to left-hand side, which is less than or equal to x squared plus 2x plus 4, then x squared plus 2x plus 4 equals to the absolute value of x squared plus 2x plus 4. Okay? So let's just be clear what I'm saying. If I can choose A so that this is greater than or equal to 0, then this is positive. And then I can just put my absolute values. And now we've made a lot of progress then.
Please repeat that.
Yeah, it's a subtle point. So if I can pick A, or if it just so happens that whatever this number is greater than or equal to 0, then anything that's greater than that is also greater than or equal to 0. So it's positive. Okay? So then that x squared plus 2x plus 4 is actually equal to the absolute value of x squared plus 2x plus 4. So if I can pick A so that this is positive or 0, then this is positive or 0, and I can just put my absolute values and I'll have it less than some number.
Does A have to be a positive real number?
Yes. Why? Because we started out saying that we want it to represent the distance between x and 2. And so for it to be a distance, it has to be greater than, it has to be positive or 0, and we don't want x to equal 2. So we want it to definitely be strictly greater than 0. So in this particular example, this expression looks a bit complicated. In some other examples, keeping A arbitrary is going to help you a lot, because you'll see, okay, I can't pick A equals 1. I have to pick A equals a half or something like that. In a lot of examples, just starting out with A equal to 1 might be easier, but I'm just showing you how would you do it in general, okay, and why does it work, okay? It works because we were just saying, what if x is close to 2? What does that all imply? Well, let's rearrange it all so that we get something that looks like what we wanted. But we know that we're not looking for this less than a positive number. We're looking for absolute value of this less than a positive number. So I better make sure that this thing is bounded below by 0 in some sense. Okay? Now, there are a lot of choices for A that'll do that for us. One that looks kind of useful to me is I could just pick A equals 2. Because this just goes away. And then this becomes like 4 or something. We could do that. We could pick A equals 3, would still work. If I picked A equals 3, this is always positive. And then all I have to worry about is, does this ever become the negative? We could pick A equals 4. That might be a choice. So what do we want to pick? Pick 2? Yeah, A equals 2. Okay. So let's go here. So pick A equals 2. Okay. And now, so now I might even, I don't know if it's overdoing it. Maybe for the first time, I'll just kind of quickly redo what we did with A equal to 2. Okay. But what you would do is you could just sub in 2 here. Actually, no. Let me not say that. But it's going to be a little. Let me just kind of reorganize what's on the board. Actually, maybe that's the best way to do this. So altogether, we find out that x minus 2, so if x is closer to 2 than 2, then the distance between, for all the x's that are closer to 2 than just the number 2, that implies that, that 4, this is the left-hand side of my inequality, down here, is less than x squared plus 2x plus 4, which is less than, and now I just work this out. So I have kind of 4, 12 plus 4. Do we get 16?
Wait, A is 2, right?
Yeah.
So that is 4 squared 16.
Oh, sorry,
Eight
32 maybe?
4 plus 4 is 28.
28. Third time's the charm. 28. So 4, 16, 24 plus 4, 28. Agreed. Okay. So we have this. Now we can erase what we had down here. Right. And then this implies, as by our argument, because this is greater than 0, this whole thing is positive. So I can just put absolute values. And now we've made a lot of progress. Do we see why I said kind of step 2 is typically the hardest part of these problems, maybe? At least sort of conceptually, there's a bit of algebra in there, and just sort of conceptually making sure that we're actually happy that I can run through this argument. Okay. Now, let's remember what we were doing. We needed to bound this factor, and we needed to bound this factor, and then we knew that we could sort of bound the overall thing. So here's the bound for the one factor, so now we have to do the other one. And it may seem funny because the other one looks like it's sitting here, but we'll deal with that. So let's kind of just draw a line. So this is almost like one idea on its own. All that work just showed us that if this is true, this is true. But it was work that was worth doing. Now this is just kind of next. Okay. And you'll see also why did I use capital A when I did this whole argument. I really want it to feel different from this next step, which still involves that same, a factor that looks the same, but now we want to figure out how to involve epsilon. Okay. So next, we want to say something like, we'll do it in just a second. I just want to write one more kind of inequality. So we would say we could also consider values of x such that mod x minus 2 is less than epsilon over 28. Okay?
In class, they said we should choose a delta, which is the min of...
Coming next. Yeah, absolutely. So this is your one inequality. This is your other inequality. Here your delta is 2. Here your delta is epsilon 28 over 28. And what we want to do is we want to claim that I can pick an x so that this is true. I can investigate when x, I cannot pick an x. I can investigate what happens when there are x's such that this is true. I can investigate what happens when there are x's such that this is true. Okay. If the x's obey that inequality, then the x's obey this inequality, which is useful to us. If the x's obey this inequality, well, it's also kind of obviously useful to us because it's sitting there. But we want the x's to obey both inequalities at the same time, so that when we multiply this guy by this guy, we get to multiply these two and get our epsilon. Okay, so that's the min argument. And so we'll lay it out carefully now.
If both of these inequalities are true, then we can multiply.
The left-hand sides and the right-hand sides. We can say that the product of the left-hand side is less than the product of the right-hand side.
Oh, so with that x minus 2 is less than 2, we don't use it when we are assuming that it's true. We use what it means.
Exactly.
Multiply.
Exactly. And that's where the confusion comes in often. It's like, why is that thing there, but this thing, and then, do you see? But the point was, we always knew we were going to be able to bound this factor because it depended on delta in some way. So we'd have a lot of freedom over it, so we do it at the end. This factor was a mess, so we wanted to kind of relate this factor to that other factor. But that's why I chose capital A. I don't use like an epsilon or anything like that because I don't want to mix that up with this final argument. Okay? But let's write it out carefully just so we're 100% happy. Okay, so we can write like proof. Okay. Suppose we are given epsilon greater than 0. We start there. We've shown that sorry, let me not write that. Sorry. What I'll say is let delta be defined as the min of 2 and epsilon over 28. Okay. Then x minus 2 less than delta implies 1, that x squared plus 2x plus 4 is less than 28, and 2, that x minus 2 is less than epsilon over 28, are both simultaneously true. Okay? Now let's just be 100% certain why that's true, okay? So what I'm saying is, if I find some x, any x that satisfies this inequality, then since this delta is defined as the minimum of these two numbers, it must be that if this guy is less than this delta, which is the minimum of them, this guy is less than this, okay? Because the minimum is always less than or equal to these, okay? So then this guy has to be less than 2, so I get that first inequality. And this guy is less than delta, which is the minimum, so it's also less than that. Okay? You could really, if you just the first time you see it, you could, if you're not 100% convinced, you could really sit down and convince yourself. You could say like, suppose it's true that this one is less than that one. Okay? Then the minimum is just equal to this one, is equal to 2. If 2 is less than this, then the minimum is 2. And then you would have something like mod x minus 2 is less than 2. So that inequality is true. And then you'd also have that mod x minus 2 is less than 2, which is less than that, so you'd have that inequality. Okay? And we could do the reverse case. We could say, oh, what if this one was less than that one? Same thing's true. Okay? So delta is always less than or equal to either of these numbers, so we get two nice inequalities chains where x minus 2 is now less than that, and mod x minus 2 is less than that. And we showed what happens when that's the case. If mod x minus 2 is less than 2, we get this, and if mod x, and then this one is just another useful inequality that we wrote down. So these are now both simultaneously true for any x that satisfies this. Okay, so we've found our delta. Okay, and then you know what my last step is, right? We're gonna just multiply these two so that we can multiply those two. And I'll write it out really carefully. So, altogether, we have that mod x minus 2 less than delta implies, I might even want to write that there exists a delta, maybe just if you wanted to be really, really careful. So we've actually shown there exists a delta such that mod x minus 2 less than delta implies that mod x cubed minus 8, which is equal to mod x minus 2 less than x squared plus 2x plus 4 is less than, you can apply them both at the same time or one by one if you wanted to. Let's say 28 mod x minus 2, which is less than 28 times epsilon over 28, which equals to epsilon. I kind of wrote it out in several steps just so that we hopefully feel comfortable with this. And this delta definitely exists because we know that the number 2 exists, and we know that given our epsilon, epsilon can always be divided by 28. So we've actually literally constructed a delta that makes it so that this whole thing works. Okay? And actually the strategy we used is pretty general. The part that gets messy is step 2 in that kind of 3-step program. It's like step 2 is where it could get messy. What if the process of bounding parts of the expression that aren't obvious gets difficult? But aside from that, this whole sort of layout is pretty much true, or it's pretty common.
Particular 11, could you do one?
Question 1. Question 1A.
No, one B, C, D.
I don't know if we'll have time to do all of them, because there is one other topic I'd like to do today, but we can do maybe one of those 3, and then like C. Okay. Was that the one with division, I think? I'm definitely happy to sort of answer questions on it, and I think, do you have solutions for them yet? Maybe if they're not out, they should come out soon. But so hopefully having done this and then talking through one of them, then when the solutions come out, you can look over the other ones, and then if you still have questions, then next week, definitely, or in the tutorial on Thursday or Friday this week. Let's see. Any questions on this? Because I think now we've kind of belabored the point. Let's see. So what was our preferred question? Was it C?
C.
Okay, yeah, we can do C. Any objections to C? Did we write this all down, or can I erase? Or maybe I'll start erasing this part. So this goes tutorial 11, so 11Q1C. Okay. And we're asked to show, I'll just kind of skip right ahead and write it up in the corner because I know I'm going to be doing that, that the limit of x as x goes to 3 of x f of x, oh sorry, I should write it out a little more carefully because we have a, so we're asked, given lim as x goes to 3 of f of x equals to 2, was it? Show that the limit as x goes to 3 of x f of x is equal to some other number, 6. All right. Okay, so that's what we're asked to show. We're given this. Maybe I won't do that. We're given this, and now we need to show this limit. Okay. So what's the first thing we're going to do? We're going to write down what we need to prove. So we want to prove, or we want to show, that for all epsilon greater than 0, there exists a delta such that x minus 3 less than delta, because we're doing the limit as we go to 3, implies that x f of x minus 6 is less than epsilon. Okay. Now, these problems are just a slight variation of what we talked about, because what we talked about was just directly showing some limits of functions, which meant we had an epsilon inequality, and all we had available to us was a delta inequality, so we had to rearrange the epsilon inequality to look like the delta inequality in some way. In this problem, we have all of these problems, 1a, b, c, d, we have no hope of doing that. Why? Because we don't know what f of x is. Okay? But the strategy is going to be very, very similar. The thing we need to just realize is that we're given something in the question. So instead of in the previous little work through that we did where we're going to rearrange this to look like something we know, what we're going to do is rearrange this to look like something we know. Okay? So, and if you've worked through kind of part A of this question, that should become more clear. That just, there's no way you can show that this is true without somehow using this. Okay? The other thing is you could convince yourself that it's pretty plausible that, like, if I just sub in x for 3 and f of x for 2, I get 6. But we really want to show that. Okay, so our goal, so maybe I could expand my previous 3 bullet points to say, like, in part 1, write down what you want to prove and what you already know. So we also know that for all epsilon greater than 0, there exists a delta, and these really don't have to be the same epsilons and deltas. So I don't know how to kind of indicate that better. I could introduce more notation, but maybe I'll just say that these don't have to be the same epsilons and deltas. This is just, we want to show this, and we know that this is true. Implies that, okay, or I could say we're also given, okay, so I've just written down the definition of the limit of f of x being 2. And so our goal, rearrange mod x f of x minus 6 to look like mod f of x minus 2. Okay?
So we're gonna
take that x minus 3 is less than delta, choose a delta which is going to make x less than 3, because it will be 3 f of x minus 6, and if you take the 3 out, and then it will be f of x.
I'm lost.
No, I'm asking
Yeah.
the way you are going to approach this, when you try and choose, using that inequality there, when you try and choose a delta, that one.
To bound this.
No, yes.
Yeah, you want to use this to bound this?
Yes.
Yes, we will end up doing that.
Okay.
It turns out there's a way we can rewrite this expression to save us some effort, but that would be the sort of, if I didn't know what to do, that's the way I'm going. In fact, if you recall last week, I tried to show you a more general way of just saying, like, what if I never know what's going on? Like, what if I can never rewrite the epsilon inequality in some clever way that allows me to do that strategy? How would I go about the problem? And I got stuck and I wasn't able to finish it, but I do actually know how to finish that now. I can show it to you, but it's sort of lengthy, and I think that most of the problems you're going to get in this course are not going to kind of need that kind of level of brute force. But what you're saying is definitely right. Okay, so our goal is to like bound this whole expression, so we're definitely going to have to study the behavior of x. How do we just study the behavior of x? Using this. How do we study the behavior of f of x? Using this. We're given something about how f of x behaves, and then this is the part that tells us about how x behaves. In the previous problem, we knew what f of x is, so we didn't need this part. Okay, if that makes sense. That's maybe another way of saying it, but yes. Now I'm just going to rewrite it quickly so that doing that, the part where we study how f and x behave, is going to be easier. So one thing we can notice, and this one's a little bit out of left field. You haven't really seen a lot like this before. But whenever you have sort of like your domain values times your kind of image values, I've just seen this a lot of times before, but what you often want to do is add and subtract something so that you can add and subtract two things that are equivalent to 0, so that you can factor this in a clever way. So saying it in words probably isn't that clear, but let me just show you. So notice that x f of x minus 6 equals to x f of x kind of minus, let's say, some constant c times f of x plus c f of x minus 6 for any c element of R. Okay, you'll see why I'm doing this, which is equal to f of x times x minus c plus c f of x minus 6, okay? And now, what was showing up in our expressions, x minus 3, so I actually want c to be 3. So, which equals, and I'm going to write here, c equals 3, f of x, x minus 3, plus, and if this were 3, I can factor out 3 times f of x minus 2. Okay. Now, this looks a little out of left field if we haven't thought about just adding and subtracting stuff so that we get a nice factorization. But this is kind of one way of getting... You have a problem because the x and the f are together. So it's like, how can I kind of almost get them apart in some sense? Now, you're not really getting them apart, but you're factoring the f out of something that you know how it behaves. You know how x minus 3 behaves because that's what appears. We know that we can derive inequalities involving that. Now, if we just started without doing this little trick, I think we could still get there. I think it would work in the end, because we'd still just have to just study how does x behave and how does f of x behave, and then involve 6 in some way. So we could probably get there, but this is just like going to get us there a lot faster. And it's a technique to be aware of. I don't know how often they just straight in a test give you a problem where you have to like add, subtract, something like this, but it is worth being aware of. But perhaps in a comprehension style proof, they'd say, how did you go from here to there? maybe they give you this line and they give you this line. How did that happen? Okay. And the hint would be, well, you'd multiply this out and notice that what were you left over with? Okay. So what did we learn from all this?
So if we don't know this trick, can we?
I think it would work. I can't tell you all of it without trying it.
Okay.
I haven't tried it, so we can try it. We're not going to have enough time to do it like today, but I suggest try it at home. See if you can repeat the stuff that we did before. And all that changes is you're going to need to bound this, and you're going to need to bound this. You're going to have to study how does f behave, f of x behave, and how does x behave. The delta inequality is going to help you with this one. The limit of f of x equals 2 is going to help you with this one. And then you might have 2 or 3 different deltas, like a delta 1, a delta 2, a delta 3. And you take the min of all of them and then combine everything in the right way. I'm not sure. But it should work. It should be possible. The question is just whether, like, how hard is it and does it break up into cases or not? It might be really, really direct. I'm actually not sure, just staring at it. Probably, I want to say that it doesn't seem like it would be too hard because it's just a factor of x. And usually rearranging an inequality involving x is not too bad. But, okay, you have a minus sign. Okay, not sure. Okay, so what do we learn altogether? We learned that, remember we were studying this, and we learned that that's equal to f of x, x minus 3, plus 3 times f of x minus 2, okay? And we want this whole thing to be bounded by epsilon. So what are we going to do now? It's going to be triangle inequality. That's 3 mod f of x minus 2. Okay? So how did I know I had to do that? Well, I want absolute values around this, and I want absolute values around that, because those are the two things that are available to me. I know I have an inequality involving absolute value of x minus 3 and an inequality involving absolute value of f of x minus 2. And the triangle inequality is always lurking around as a tool. So this is now looking pretty promising. We know that we can probably do something about this. We know that we can probably do something about this. The only one left over is that f of x. Okay? So what are we going to do about that? Exactly. So now we're going to almost like, I want to just put it aside from the whole epsilon discussion and just say that we know that lim x goes to 3, f of x equals 2, implies that there exists a delta such that, and I'll say actually this delta depends on a, okay, such that x minus 3 less than delta a implies that f of x minus 2 is less than a. Okay? So I've just written out the definition of the limit, of this limit, but I've used a instead of epsilon, capital A. And I want to do that just to keep it separate from the epsilon that we have to use in our proof. Okay? And I give a little subscript just so I can keep track of this. You don't have to do this, but it is useful sometimes. Okay? And we want to rearrange this to learn something about that. So again, this is that same thing. This is like part 2 of our 3 bullet point thing, where we have something we know about, we have something we know about, we have something we don't know about. So we use what we already know to try and derive an expression for that. Okay? And so this is just equivalent to this guy, just continuing over here, is equivalent to saying that 2 minus a is less than f of x, which is less than 2 plus a. Okay? So, and then again, I don't want to study f less than some positive number. I want to study mod f less than some positive number. So I want this guy, I want to pick a value of a so that this is positive, which forces this to be positive, so that I can just put my absolute value. So what should we choose a to be? We could choose 2. We could choose 1. We just shouldn't choose anything bigger than 2. Okay? If we choose something bigger than 2, this is negative. Now we don't know really what's going on with f of x anymore. That also kind of makes sense if you think about what we're doing here. We're saying we want f of x to be close to 2. So if I choose a too big, I might screw things up. So, so what should we choose? A is 2, 1. Don't choose 3 over 2, please. Don't choose 2 over pi. I don't want to do that. Yeah, okay, so we choose a is 1. So notice a equals 1 implies that there exists a delta 1 such that, I'm going to really write this out again just to emphasize the point, such that x minus 3 less than delta 1 implies that 1 is less than f of x, which is less than 3, which implies that mod f of x is less than 3. Okay? That's sort of the whole argument in one go. If we had just chosen 1 from the start, whenever x is closer to 3 than whatever this delta is that we're guaranteed exists because of this limit, then we have this inequality, and as we spoke about, that means that this is positive, so I can just put the absolute values and now have a nice bound for my mod f of x. Okay? So now we just have to put the puzzle pieces together carefully, because we know we can bound this and this, and we just found that, so now it's like just carefully put it all together. So I'm gonna, I think, write it out over here, just the thing I want to keep track of, which is that mod x f of x minus 6 is less than or equal to mod f of x mod x minus 3 plus 3 mod f of x minus 2. Okay, this is just sort of so I don't get lost. And now we're going to write out a formal proof. You might want to take a few more steps to just really write down your inequalities that you kind of need for this one, for this one, and for this one, just so that it all works out. But I'm going to kind of try to skip ahead in the interest of time, but it should make sense in your notes. So, formal proof. Let epsilon greater than 0. Okay, no waste right there. We need our delta 1 that we showed existed. Let's just think about this carefully. So probably what I want to do is I want this factor to be less than epsilon over 2, and I want this one to be less than epsilon over 2. Okay, so I'll write out several things here. So we know that lim x goes to 3 of f of x equals 2 implies several facts. Okay, so the first fact is that there exists a delta 1 such that mod f of x, such that mod x minus 3 less than delta 1 implies that mod f of x is less than 3. Okay? Fact 2, let's see, so then we want this one to be less than epsilon over 6. So there exists a delta epsilon over 6 such that x minus 3 less than delta epsilon over 6 implies that mod f of x minus 2 is less than epsilon over 6. Okay, that's me handling this factor. Okay, and then okay, we could also just, and we want these ones to be less than epsilon over 3, right? We seek mod x minus 3 less than epsilon, over 6, I believe. Okay, this one, not to mix everything up, is to handle that guy. Okay. So I want all of these to be simultaneously true. So we use our min argument. Choose delta equal to the min of, I need delta to be the min of delta 1, of delta epsilon over 6. Remember, we're guaranteed that both of these numbers really do exist, and this number, epsilon over 6. Okay. Then x minus 3 less than delta implies that 1, 2, and 3 are simultaneously true. And we just combine them all together. So that implies that mod x f of x minus 6, which equals to, we agreed is equal to f of x mod x minus 3 plus 3 mod f of x minus 2 is now less than this one was less than 3, this one was less than epsilon over 6, so it's 3 epsilon over 6 plus 3 epsilon over 6, which equals epsilon. Cool. So lengthy, but I think really drives home the point of the, okay, you'll probably never get a question more complicated than this, but in practice, the idea from here on out is kind of like easy to generalize. It's like, I need to look at what I want, I need to bound each part of the expression, really prove that there exists some delta that does that for me, and then pick the minimum of the deltas so that I really just, in the domain on the x-axis, I'm going close enough to 3. I'm making sure that for all the x's closer to 3 than all of these numbers, I get all of my inequalities true, and then the final result that I wanted to show that this is less than epsilon is true. Okay, any questions there? And then I would say maybe, you might actually save time by not doing this. The minus sign might mess you up, but trying to, what we discussed of like adding and subtracting something to get this. maybe you could just put together an argument without that. I encourage you to try it at home. But at least, hopefully now we kind of know what's going on with all these different deltas, why did we use them in argument, and what is the structure in general that I should pursue to solve a problem that I don't know how to do.
Could you explain again where the third?
It's this last one. Yeah, this one gets, again, this is always going to feel a little confusing because we have this kind of, we have x minus 3s everywhere, right? So this one was just to handle that factor, number one. Number two is clearly to handle that factor. And number three is that I still have this floating around. Okay, and this is the one I have to think a little bit carefully about, because in the other ones I'm bounding the f of x things. But this one feels a little funny now because what do I mean by bounding this guy? I just know that I can always pick an x close enough, x is close enough to 3 that they're less than any positive number. And so I just choose epsilon over 6 for this because it's going to multiply by that 3. Sorry, I'm not sure if that made it clear. Maybe you can tell me a little more. So I agree that this one is the one that's kind of out of place because we derived this one very carefully. We all agree on that. This one is just the definition of the limit for a particular epsilon. Well, for a particular, remember, you're just using the definition of f of x, the limit being of f of x being 2, I could get this one, right? And I just chose a particular choice for what I want it to be less than, and I know that there's a delta guaranteed for that. But this last one, remember, I had this piece of the expression that I haven't dealt with yet. I've shown that this is less than 3. I've shown that this is less than epsilon over 6, but I haven't shown how to handle that. And I don't want to worry about these things. I could just make my life so much easier by just saying, actually, you know what? Even just forgetting all of this, if I wanted to, I could pick some x's that are close enough to 3 so that they're less than some positive number. And which positive number am I going to choose? I'm just going to choose the one that when it multiplies by whatever this is less than, it makes my life easy. Does that make it a little clearer? Okay, cool.
So, with the same question, are you allowed to just choose delta to be any positive real number?
For this part?
Yeah.
Yes.
Because I thought we could choose epsilon to be any number, because if the definition says for all epsilon greater than 0, they exist a delta.
Mm-hmm.
I didn't know we could choose a delta.
If we know that that delta exists, and it's not just that we're choosing a delta, we are allowed to pick any delta. We can always just pick a positive number. They're out there, right? We just, oh, okay, what if delta is 20? Yeah. What if delta is 30? What if delta is pi? It's not that. It's we need to pick the delta that implies something.
So here with delta is equal to epsilon over 6, what does it imply?
This one.
Yes. Because I'm just like, how... We know we want that because it's going to work out at the end.
Well, the delta that we want to imply is this one. Right?
Yes, which was, we used that epsilon over 6 as well.
Yeah.
In it. So how did we come up with just choosing it to be...
This one?
Yes, that one. Like, how did we get it to be epsilon over 6? Like, what is the justification behind it, besides the fact that we know we wanted it so that it works out to be epsilon at the end?
So I guess what I could do is I could like sort of rephrase your question, though maybe I'm distorting what you're asking, but sort of there are two pitfalls to what we're doing. Like one thing we might worry about is like, does the delta that we claim exists actually exist? And then two, we might worry, does the delta that we choose actually do the thing that we claim it does?
Yeah.
We agree that this delta does the thing that we claim it does, right?
Yes.
Okay. So that part's fine. That's kind of the second part of your question. Like, how did we know apart from just picking the thing that would just work?
Yeah.
So we've done that. And so the only other pitfall is like, what if that delta just wasn't allowed to be chosen? So we could rephrase the question, could it be true that I'm not allowed to choose x's such that this? And then you can see that, well, I mean, why? Like, why wouldn't I be